Hi everyone, I'm Cheryl. In this problem, we're going to be finding the surface area of a solid generated by revolving a curve about the x-axis. In this particular problem, we're going to be revolving the curve y equals 1/3 x cubed, which is right here, about the x-axis. And I've already drawn the picture so we can kind of see what that solid is going to look like. All right, so we need to find the surface area of this solid. Well, we need a formula. And instead of just writing the formula down, I want to give you an idea of where it comes from. We're not going to actually derive the formula, but just give you a sense. All right, so we're going to begin by taking a representative element. We're going to take a look at this particular solid. I'm going to take just a little piece, and I'm going to revolve it about the x-axis. And you can see that when I do that, I get something that's called a frustum. A frustum is really just a cone where you slice off the top and remove that top cone, and you're left with this type of a solid. And again, we call that a frustum. We have a geometry formula for finding the surface area of a frustum. The formula is 2 pi times the average radius. Now remember, in a frustum, you'll have the top radius and the bottom radius, which will be different. So it's the average of those two. Then you're going to multiply it by the slant height, which is this length right here. Okay. All right, so what do? Well, we're going to find the surface area of this frustum, and then we're going to find the surface area of a bunch of different frustums as we go across my solid. And then finally, we're going to let the number of frustums that we use go to infinity. Well, that should indicate to you that we're going to be using an integral to find the surface area. So let's go ahead and write our formula down. We have the surface area is going to be equal to 2 pi times the integral from a to b of my average radius. Now, if you think about this, as we take infinitely many of these frustums, they're going to be getting thinner and thinner and thinner. So the smaller radius and the larger radius are going to be getting closer and closer together. So we really only need to talk about a radius in that part. The next piece is the slant height. Now, if you look on your picture, the slant height is going to be this length right here. And you can kind of make a little triangle out of this, and you can see that you can get, this is a right triangle, so you can use the Pythagorean theorem to help us get that slant height. Now, what it's going to end up looking like in our formula is the square root of 1 plus f prime of x squared dx. And again, I'm not going to derive that formula, but you can see that this looks like it's going to come from a Pythagorean theorem problem. Okay, so now that we have the general formula, we need to plug in the specifics for our problem. So we'll start out with our 2 pi and our integral. Well, what are the limits of integration? We'll be taking our frustums starting at 0 and stacking them up until we get to x equals 3. So we'll be integrating from 0 to 3. The next piece is the radius. Now, if you think about what the radius is in this problem, we're going from the axis of revolution out to the edge. Okay? And again, remember, this is going to be an average, but those are so thin that we're really just looking for this vertical distance. Right? Well, a vertical distance is measured in terms of y, but notice I want to be integrating with respect to x. So instead of writing a y, I'll write 1/3 x cubed. So 1/3 x cubed. The next part of the formula is our square root of 1 plus the derivative squared. Well, I need the derivative. So let's go ahead and take a look at that. dy dx is going to equal 1/3 times 3x squared, which reduces to x squared. So I'm going to have x squared dx. All right, I have my formula all set up now for this particular problem. The next thing I'm going to do is simplify that integrand just a little bit. The 1/3 is a constant multiple, so I can pull that out, and I have 2 pi over 3 times the integral from 0 to 3 of x cubed times the square root of 1 plus x to the 4th dx. This integrand is too complicated for just our basic rules, so we're going to need a substitution to help us out with this one. So oftentimes when we do a substitution, we look for a composite function, and our u value will be the inside of the composite function, which in this case is the 1 plus 4x squared. So let's do a little side work here, and I'm going to let u equal 1 plus x to the 4th. That means that du is going to be 4x cubed dx. Now, I notice that I have an x cubed and a dx in this problem, but I would like it to be a 4x cubed dx. So I'm going to multiply by 4 and divide by 4. Now I have a 4x cubed dx in my problem, which I can replace with my du. Okay, so let's see what that leaves me with. I've got 2 pi over 3. I've got my integral. And I've got the square root of u du all over 4. Okay, if you notice, for a moment here, I've left these limits of integration empty. The reason is that the 0 and the 3 correspond to x values. I have now changed everything over to u values, so I need my limits of integration to correspond to u values. Well, if x equals 0, what does u equal? Well, u is 1 plus x to the 4th. So that'll be 1 plus 0 to the 4th, which is just 1. If x equals 3, I'll have u equals 1 plus 3 to the 4th. 3 to the 4th is 81, plus 1 is 82. So my upper limit of integration becomes an 82 if I'm using u values. Okay, this is something that I can use my basic integration rules to help me evaluate. So I'll begin by pulling the 1/4 out. So I've got 2 pi over 3 times 1/4, and I'll be integrating the square root of u, which I'm going to write as u to the 1/2 power, from 1 to 82. So with a little simplifying, this is going to become pi over 6, and the integral of u to the 1/2 is u to the 3/2 over 3/2, which is the same thing as multiplying by 2/3. And then I'll evaluate from 1 to 82. All right, a little more simplifying. Pi over 6 times 2/3, that's going to reduce to pi over 9. And now I have to evaluate what happens when u is 82. So this will be 82 to the 3/2 power. And then I'll subtract what happens when I plug in 1 to the 3/2 power. Okay, at this point, 82 to the 3/2 power is not going to be a simple integer. 1 to the 3/2 is just 1, but I think I'm going to pull out my calculator to get an approximation for this value. So when I enter pi divided by 9 times 82 to the 3/2 power, and then subtract pi divided by 9 times 1, I'm going to get approximately 258.85. I hope that was helpful. Thanks.